Welcome back, everyone, to Chem 102. My name is Professor El Hawari, and today we will be going over experiment number 9, chemical equilibrium and Le Chatelier's principle. Again, first order of business, make a copy of the lab report. You are going to find it in our course document. Make a copy and start editing the document. The first thing you want to do is you want to put your name and the date in which you completed lab number 9. So the objective for this experiment, again, the direction is that you want to write at least one sentence that clearly describes the goal and the method to complete the experiment. So the objective for today is to investigate chemical equilibrium and understand how changes in concentration, temperature, and pressure affect the position of equilibrium in a reversible reaction, applying Le Chatelier's principle to predict and explain these shifts. Again, the objective is to investigate chemical equilibrium and understand how changes in concentration, temperature, and pressure affect the position of equilibrium in a reversible reaction, applying Le Chatelier's principle to predict and explain these shifts. So, pause the video, write down your objective, and we are going to move on to the next section, which is the experiment and data sheet. So write down the list of equipments that we'll be using and the functions as well. So the first equipment we'll be using is the beaker. And again, a beaker is a common lab container used to hold, mix, and heat liquids during experiments. Test tube contains small quantities of reactants or for observation of reactions. Stirring rod mixes reactants evenly to ensure consistent reaction. Disposable pipette adds precise amounts of liquids to reactants. Balance or scale measures the mass of reactants accurately before the experiment begins. Safety goggles protects the eye from splashes or reactions. So let's talk about the equilibrium reaction. This is our chemical equilibrium equation. The equation has two sides. The left side is before the arrow. This is to the left of the arrow. And the right side is after the arrow. The left side is called the reactant. The right side is called the product. A special arrow is used with equilibrium reactions, which is this double headed arrow, and this indicates that the reaction simultaneously runs forward and reverse. Now, chemical equilibrium, which is what you're seeing, the double-headed arrow, it's a state of a reaction in which the rates, speeds of the forward reaction and reverse reactions are equal. So this is a very important concept. The reaction never stops. It is always moving. The speed of the forward reaction, left to right, is equal to the speed of the reverse reaction, right to left. As the forward reaction proceeds, it is canceled out by the reverse reaction. So these are what we call equilibrium reactions. So these are chemical reactions that do not go to completion. All the reactants have not been converted to products. This is also known as incomplete reaction. So this reaction, as you can see, goes both ways. The NOCl turns into NO and Cl2, and at the same time, Cl2 is linking up with NO to give us NOCl. So it's like back and forth, it goes back and forth. Now, chemical equilibrium is similar to running a treadmill. So, this is an analogy. Now, you are going forward, but the treadmill is going in reverse at the same time. So, everything is in motion, but you stay in one place. So, this is chemical equilibrium. Now let's talk about Le Chatelier's principle. Now, if a stress is placed on a system, the system will respond by altering the equilibrium composition in such a way as to minimize or undo the stress. There are different types of stresses that you will see in today's experiment. Now, a stress could be adding or removing a substance in the reaction, That could be either a reactant or a product. You can increase or decrease the temperature of the reaction. You can increase or decrease the pressure in the reaction. So, all these are types of stresses. When you stress a system at equilibrium, it will either shift to the right or it will shift to the left in response to that stress. Equilibrium is going to shift to the right if the amount of substances on the right of an equilibrium equation goes up, and equilibrium is going to shift to the left when the amount of substances on the left of an equilibrium equation goes up. Now, how to determine the direction of the shift? Now, it depends on many factors. So, if you add something to one side, the equilibrium will shift to the opposite side to respond to that stress. So, the reaction is going to consume what was added, it will start eating it up. And if you remove something, the equation will actually want to shift towards that same side in order to replenish what was lost. And we are going to see that when we do the experiment today. So this is the system that we are looking at. 2SO2 plus O2 is in equilibrium with 2SO3. Now the question says, what happens when we add oxygen? Now, as you see, oxygen is on the left side. If you keep adding more and more and more and more oxygen, the system does not want the added oxygen. So what the system is going to start to do now, it will start to decrease the oxygen and it will shift to the right. So it's going to shift away from oxygen. So you increase the left side and the system is going to shift to the right. So we're going to say the direction of the shift for the first one is to the right. Now, what if you remove SO2? If you get rid of SO2, the system would want to make more of it. So, my question for you is, if we want to make more SO2, do we want to shift to the left to make more of it, or do we shift to the right away from it? So, the correct answer, we want to shift to the left so we can make more and more SO2. Last but not least, what if we want to add SO3? So again, if we add SO3, now we have a lot of SO3s on the right side. The system does not want that. It wants to get rid of the SO3. So if we add a lot of SO3 on the right side, the system will shift to the left away from it in order to decrease the amount of SO3 that was added. So when you add something to a side, the equilibrium will shift to the opposite side in response to the stress. The reaction consumes what was added. And when you remove something from a side, the equilibrium will shift to the same side in response to the stress, and the reaction replenishes what was lost. So it said right, left, left. Shift right, consume added O2. Shift left, replenish lost SO2. Shift left to consume added SO3. Now let's look at the experiment for today. So make sure you're filling out the data sheet. And again, the data sheet is right here, which is experiment number 9. And you are expected to fill this out. So we have reaction number 1. You're going to write your observation for CuSO4, observation for NH3. And now here you want to write observations during / after the chemical reaction. How many drops of NH3 cause a color change? What was the color after NH3 was added to CuSO4? How many drops of HCl cause a color change? What was the color of the solution after this HCl was added? And then we're going to talk about equilibrium. When we add NH3, does the equilibrium shift to the left or does it shift to the right? When HCl is added, does the equilibrium shift left or right? So this is the first reaction. Now we have a second reaction. We're going to do the same thing. And also, we have the summary. So, 2 reactions and a summary. So, let's go back to the PowerPoint and let's continue. So, in this experiment, as you can see, copper sulfate, we're going to dissolve it in water. It has a turquoise color. And when NH3 is added, you're going to see a deep blue CuNH34SO4 solution that is produced. Now, it should make sense. The more NH3 we add, NH3 is on the left side, the more of it we add, it will shift away from it. So it's going to go to the right to make more of our product. So NH3 is removed by chemically reacting it with hydrochloric acid. And we're going to see what is going to happen. Acid and base will neutralize each other. All right. The second experiment we're going to be studying is the FeNO33 plus NaSCN. FeNO33 has this nice yellow color. The reactants have a yellow color and the product have a blood red color. So if we add more and more NaCN, what would you expect the color to be? Very good. It should be red because it's shifting away from the left side going to the right side. So it's going to be red. So we're going to see what's going to happen to these two systems by showing the video of the experiment. So again, here is the experimental details. We got CuSO4 plus NH3 giving us CuNH34SO4. And we also have FeNO33 plus NaSCN giving us FeSCN2 plus NaNO3 plus NO3 minus. We're going to start right away by watching the experiment and then answering the question. So first it says add a few milliliters of zero point 0.1 CuSO4 solution to a dry test tube, and then two to the test tube with CuSO4. Use a pipette to add 1 molar NH3 dropwise. So you want you to count the drop here of each one. So now we have copper sulfate has a turquoise color. All right. We want you to count the drops. So it was added all at once. So we're going to say this. So we're going to say this was, let's see if this was added. It's going to be added dropwise, which is the ammonia. Before we add, so let's see, before we add now the ammonia, uh, what do we expect? So the turquoise color, is it gonna stay turquoise or is it going to be this deep blue color? So the more NH3 we add, again, it will shift to the right. So we should be getting this color. Let's see if we're gonna get this color. Let's see if we can. Is it gonna be drop by drop? So the ammonia, is it gonna be added drop by drop? All right, good. One. This is the first drop. See, it's still not. It's still turquoise. Two, still turquoise. Three, four, still look at that. It's turning deep blue. Five. Now we gotta shake it to establish equilibrium. Six. All right, so this is the number of drops you gotta be at. All right, look at that. Six, is it gonna stay, or do we need one more drop? Maybe one more drop. Seven. All right. You see, so this shows us we start with a turquoise color, and if we add more reactants, it will shift towards the product side. So you would say adding NH3, this is in your lab report now. So adding NH3 is going to give us a right shift. It will shift to the right side, and we added 7 drops of NH3. So when you add reactants, when you add something to the left side of the arrow, it will make you shift to the right. All right. Let's see. So this is what happens. You got, this is the copper sulfate. This is your reactant. This was ammonium hydroxide, which is going to add the NH3 here. When you add more of this, it will give us product, and the color of the product is right here. All right. Now let's see what happens when we add hydrochloric acid. Now, hydrochloric acid, when we add it, it will start removing NH3. Now, this is a system at equilibrium. When you remove NH3, the system now feels very sad. Why? Because when you remove it, the system wants to make more of it. So how do we make more of it? Do we shift to the left towards it, or do we shift to the right away from it? So that, let's see. So the system is going to, we say, will shift to the, well, let's see the color. If we get a turquoise color, that means it's shifting to the left. If we get a blue color, that means it's shifting to the right. So let's play the video, and we're gonna learn something from the video. So we're gonna now take our, so now look, our, the equilibrium now is right here because it's deep blue color. So let's add hydrochloric acid and again count the drops of the acid. So we don't care about the CuSO4, but we care about the drops of hydrochloric acid. So we're gonna add it drop by drop. All right, one drop of acid, nothing happens, not yet. A second drop of acid, nothing yet. A third drop of acid, nothing yet. A fourth drop of acid, so the equilibrium is still to the right. Five drops of acid, still. Six drops of acid, seven, eight, nine, 10, 11, 12, 13, 14, 15. And notice it's getting lighter. 16, 17, 18, 19. It's getting very light. 20, 21, 22, 23, 24. And notice it's becoming turquoise. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Look at that. 35, 36. All right, and the experiment is look at that. It's over. We're back to the original color. So again, the summary is if we remove NH3, so hydrochloric acid is essentially removing the NH3. You get rid of NH3, the system is gonna shift towards NH3, so it's gonna shift to the left. So this is what happens before and after. The more HCl you add, the more NH3 is removed, and the system is going to shift to the left to make more NH3. Let's talk about the iron thiocyanate system, and it has different colors. The ferric nitrate, it has a yellow color, and then we have the iron thiocyanate, it has a red color. That's the product. So let's do the experiment with this system. All right, so we're starting with a beaker. We're gonna we're gonna take a pipette, and we're going to add 10 drops of the ferric nitrate. It has a beautiful yellow color. We're gonna add it to some distilled water, some water. So you can see one. Uh, all right, 10 drops of it. And then we are going to add the sodium thiocyanate, the NaSCN. So if you look, if we add these two reactants, what do we expect to see? We expect to see let's see, if we see red, that means it's shifting to the right. If we see yellow, that means it's shifting to the left. So again, let's see the video. We're now going to we took the yellow, all right, and now we are going to take the sodium thiocyanate. Let's see, what color is it turning? We gotta put 10 drops. If it's turning red, that means it's shifting right. If it's turning yellow, that means it's shifting left. Now we're gonna swirl the content and see what we see. All right, look at that. It's like a magic trick, and we see it's becoming a little bit. You can see it's reddish. It's a little bit red. So when you add sodium thiocyanate, it's still yellow because we added, a lot of FeNO3, but because we are also adding the NaSCN, we did see some red, which means it's shifting to the right. So this is when we shift to the right. Now we're gonna try. Yeah. Now this here we're just creating the FeNO3 solution, but you did see some red. But here is the actual experiment. We're gonna have 4 test tubes, A, B, C, D. Now this was the stock. It is yellow and it is a bit. You can see a bit reddish, but it's mainly yellow because this is our stock, and we're gonna do the experiment now. So now we're doing the experiment. We're going to be adding um, the reference solution, which is the stock solution. We're going to add 15 drops of this reference solution into ABCD. Test tube A will be our reference, and then we're going to compare it to what we see in B, C, and D. So, again, this is just for reference. So, we created a stock solution. It is mainly yellow, but I do see some, it's mainly yellow, but there is some red. It's not pure like sun yellow. The reddish product is making the yellow a bit darker. Good. So we're adding 15 drops. So now B, C, and D will be our experiment. So in the next videos, we'll see what we are going to be doing for B, C, and D. All right, we added our drops and we are ready for the experiment. Okay, first experiment. So now we have A, B, C, D. A is our reference. B, C, D will be doing the experiment. And let's see now what we are going to be doing. So to test tube B, we're going to use a clean pipette and add FeNO33. So we'll be adding more reactant. For test tube C, we will be adding NaSCN, which is the second reactant. For test tube D, we'll be adding NaNO3, which is our product. And let's see what's going to happen. All right, so let's play the video. So we're going to take B and we're going to add FeNO33. Let's see what's going to happen when we add FeNO33, which is a reactant. What is the direction of the shift? So we should expect, let's see what we see first. What do we see? FeNO3, and the direction shifts. See the color. The color is very important. Let's see. Look at that. It's becoming much, much, much more red. See? So you add something on the left side. You add a reactant and it shifts to the right. So for B, it's a right shift. So make sure to write that in your lab report. Let's look at C. C, we're gonna add NaSCN, which is the other reactant. Let's see, is it gonna behave similar to FeNO33? Is it? So let's see. If we see red, that means it's a right shift. Let's see. Let's add it. We're adding it. If we see red, it's a right shift. If we see yellow, it's a left shift. Let's swirl it and look at that. It's not as the first one, but it's actually turning a little bit. It's still staying yellow. The second one actually is a bit reddish. It's still red, so the second one is a right shift. The third one now, the third one will be adding NaNO3, which is a product. So the summary here so far, if you add one of the reactants, it will shift to the right. We were able to see a much better observation for the FeNO33. We did see a very dark red color. For the NaSCN, we did not see as much, but we did shift to the right. Now, for the last one, we're going to be adding a product now. NaNO3 is on the right side. So again, if we add it, we expect it this to go to the left and stay yellow. But let's see. Is it going to be more yellow or is it going to be red? So we're going to be adding it to test tube D. We'll be adding the drops, 5 drops. Very good. One. Very good. As you can see, now this is clear. We're not seeing any red color. This is very clear. So this shows us that it's shifting to the left. So we're not shifting to the right anymore. We're shifting to the left. So for test tube, again, BC, it's a right shift favoring the product. For test tube D, it's shifting to the left, favoring the reactants. Very good. And here are the experiments. Again, FeNO3 became red, shifting right. The NaSCN also, you can see it better here. It did not show, well on the video, but the NaSCN is red, so it's going to shift to the right. But the NaNO3 stayed yellow, just like the control. So we say it's a left shift. Now we're done with the experiment, so fill out all your data sheets. And in one or more paragraphs, you want to summarize the results of this experiment. Write in full sentences, avoid using bullet points or sentence fragments. Describe any trends or patterns you observe. Make an effort to support your statements by referring to the theory in the pre-lab discussion. For instance, how could you tell when there's an equilibrium shift? How can you tell if the shift is to the right or to the left? Support your statement with examples from your data. So thank you. The announcements now. You are expected to complete the following by the assigned due date. Watch the assigned experimental video, which you did. Complete the quiz based on the experimental video on Brightspace and submit the lab report using the given template based on the experimental video. Thank you and see you soon.